What's up, class? Oh, it's my cat. As I said in the last video, I'm pretty sure with where we're at right now, we're done talking with derivatives, kind of. So, for where we're at in calculus right now, I don't have any new derivative techniques to show you. We know everything we need to know to kind of get a basis on calculus and a lot of the applications of calculus that are conventional in many, many subjects and within mathematics itself. So we're going to talk about kind of a, maybe for some of you expected, for others maybe unexpected, kind of opposite or contrary to derivatives. We have areas. Areas we've been dealing with since very, very young ages. But this is calculus. We're dealing with infinitely small and infinitely large things. So we're going to be talking about infinitely small areas. So we're going to kind of going to go into the world of integration, if you've heard of that before, taking areas of graphs with a lot of techniques. Integration is a whole new can of worms of calculus. Many of you will justifiably hate integration, which is pretty understandable. Integration is definitely not the easiest part of calculus. Probably one of the hardest things many will have to use in their lives. Integration in the process of finding areas of functions that are not boxes, right? So how do areas, slopes, and functions all relate, right? If you think of a graph, and I have this graph here drawn that I'll use throughout the video. Cat. Okay. We're not going to be there yet. Right now we're going to be here kind of bottom left. Very, I'll draw kind of a small graph of just a linear line. And I'm going to draw a graph of kind of a parabola, and then maybe just a graph of a straight line. That'd be a y equals, and then just a number like 2, for example, right? I'm actually going to say this is going to be x squared, this is going to be 2x, and this is just going to be 2, right? You know, with derivatives, you could probably pretty quickly identify that the derivative of this function, x squared, is going to be 2x. Derivative of 2x is going to be 2, right? But early mathematicians discovered that we can go the other way with derivatives, right? We can take antiderivatives of functions very similarly to how we can differentiate, we can integrate to go backwards in this kind of continuity of calculus and all of that, whatever. We're going to eventually get to later videos of which we're going to find out, you know, if you integrate 2, you're going to get 2x. If you integrate 2x, you're going to get x squared, right? And initially it's going to start off pretty simple, and then we're going to get into a lot more difficult, kind of abstract ways we can integrate functions, clever tricks, and a lot of applications of integration, right? But really, why does this work? We think of derivatives as instantaneous slopes that can be kind of evaluated at any point of a function, right? And a derivative is going to give us a slope value, right? But with integration, we can't simply plug in a value. We sort of can. We'll get more on that later, not in this video. But you can't simply say like f prime of 2. That's going to be a with integration and areas, we take areas over an interval, because really what areas are in calculus, and this is a big thing, is areas show us accumulation of change. And I'm going to use this graph over here, this kind of starting at this x value and the ending at this value. We're going to have an area in between, right? And I'm not going to fill in the entire area there, but what an area in calculus is showing us is an accumulation of something. We're going to be accumulating area, like we're accumulating mass, or we're accumulating distance, speed, anything like that. With derivatives, we're dealing with slopes. With integration and integrals, we are dealing with accumulation, right, acquiring. So I'll kind of reiterate this because this is a very, very confusing concept to conceptually understand, right? I'll draw a slightly bigger graph here and go back to kind of a probably familiar example, right? So maybe in chemistry or physics, you've dealt with like rates and time. If you were to think okay, if I travel at 2 meters per second for 4 seconds, how much distance will I have traveled in that 4 seconds? Well, if I draw a graph of just velocity v as a function of time, velocity is just simply equal to 2, right? And this is going to be at v equals 2. We are traveling at 2 meters per second, and that's a constant value, right? Not changing anything with time. So if you want to answer my question there, we have 1, 2, 3, 4, 5, 6, 7, 8, or however far you want to go. My question was, if you travel at 2 meters per second for 4 seconds, how far would you travel? Well, in the past, you would multiply 2 meters per second times 4 seconds, right? And then you'd have some units cancel out, and then you'd get 8 meters, right? Well, we figured out pretty early on in math that if you this multiplication process is very similar to how we find areas of geometric shapes, right? If I were to just kind of evaluate this area of v equals 2, but then kind of on an interval from 0 to 4, kind of as I've roughly highlighted there, you'd kind of acquire this area, right? As you see there, we're taking the area of a box. But what we're really doing is we're taking the area that is between this line, v of t equals 2 meters per second, the area between that line and the x-axis, or in this case, the t-axis. This is v of t, not v of x, right? If we were to find the area, pretend this is a box, we'd be multiplying 4 by 2, and we'd get 8, right? And so we take the area of this box and get 8 meters. And the units work because t is measured in seconds, and 2 is going to be measured in meters per second, right? So very similar to how you would do this in chemistry or physics class. We're going to multiply rate by time, and we get a distance, right? So not much changes in calculus, except it gets a whole lot harder. We're not going to be dealing with straight lines for very longer. We're going to be dealing with functions that look like that, right? So in this video, we're going to specifically talk kind of about a little bit of a history lesson of areas in calculus. We're going to talk a little bit about the math. In the next video, we're going to get into some more calculation-based and experimental methods of calculating areas in integration, right? So the idea of integration revolves around finding areas, and we kind of, by relating that, rates times time will get you a distance, we can find that kind of a function output value multiplied by an interval of input, or a change in input value, kind of like a delta x, right? In this case, it's actually going to be a dx. We'll get into that more later. But multiplied over by an interval, you can get an area of a really, really goofy curve or shape, and that gives you an accumulation of something. In that example I showed you there with 8 meters, as a distance, we accumulate a distance over an interval of time, kind of by integrating a velocity, right? We accumulate a distance by looking at distances, kind of a spoiler, derivative, because remember, if you look at displacement, we talked about displacement a while ago in distance. If you look at displacement's derivative, velocity, or distance's derivative, velocity, if you kind of take the area of that velocity graph, you're going to get a distance value over an interval, right? So let's kind of do a little history lesson here. Again, I'll kind of use graphs to help me along. And like I've said a million times, mathematicians early on figured out that we have very simple functions, and we can take the area of these functions to convert them into distances or accumulations of mass and all that stuff, right, over a time interval. But eventually, we kind of had, we had to deal with more complex functions, and so we came up with ways to find the areas of those, and we started off very crude, and we got very, very advanced, and we found patterns, much like we did with derivatives. We came up with tricks and rules and formulas that helped us tremendously, right, and allowed us to advance greatly in many, many fields, right? But before we go on, I kind of forgot to explain something. We talked about how we took the area of that velocity graph and we got a change in position, right? We got an accumulation of distance, right? I'm going to go ahead and draw that velocity graph again, right, of 2, right? And then, you know, if we were to talk about our position, what we'd actually see, it's going to look something like this. That's a straight line. That's my best attempt at a linear graph right there. What you're going to see happen is, well, and you may be asking yourself, why does this work? Why does taking an area, and we're going to get into more abstract functions, why does taking an area kind of get us different functions, kind of like how derivatives do, right? If you were to take the slope of this line, you would get 2, and we can represent 2 graphically with a straight line, and that's pretty straightforward, but going backwards, it's really, really difficult to understand, right? And I might want to use a separate example of kind of integration, right? You can take the area of this linear line and get somewhat of a parabolic shape, right? And if you were to really think about how that works, how we kind of do this transformation, what you're going to do is when you're accumulating, this would be f prime of x, and this would be f of x, right? Whoa, I totally butchered that. I should have looked at the board. F of x, right? What you see is when you're accumulating change on your derivative, think about it as your derivative is growing. It's accumulating change. And so what's happening is your slope is going to be growing, growing, growing as your derivative changes. And those little tiny infinitesimal accumulations of change in your derivative are going to kind of influence the curve of your function, right? So kind of, if you were to think about here, we're accumulating some change on our derivative, and our slope here is going to be changing, right? I just kind of drew a bunch of tangent lines there. Sorry if that was a bit difficult to see, but the key takeaway is that they were increasing in slope as your derivative was increasing in value, but not just increasing in value, increasing in area, because those two are different. There are, we can have discontinuities, we can have, kind of spoiler, we can have negative areas that get really, really weird really fast. It's just negative areas. But we see as this accumulation of area actually is going to directly influence kind of our the change in slope of our graph, right? And I'll kind of re-emphasize that as we learn more and more about taking areas of functions, because it's kind of a key concept, and it's really difficult to conceptualize and like think about, okay, how does accumulating area on one function correspond to a change in slope of another, and how does that change of slope influence growth rates of a function, right? Because higher slope, you're growing faster. Okay, so we're going to talk about, and I'm going to kind of draw a copy of this graph over here, just on a different scale, and it's going to be a bit curvier here, right? So eventually we wanted to take, as mathematicians, areas of functions that looked something like this, right? But we didn't have modern integration methods or ways at the time, very early on in history, to do so. So we do what we do a lot in calculus, and we approximate things. We get pretty darn close to the actual answer, and we can make inferences about the actual answer, whether it's an over or underestimate. We've talked about this a lot in the past. One of the big applications of mathematics and calculus is approximating things. And so what we really did at the very start of calculus is we would take strips of a function. We would take boxes. We would literally draw boxes on our function and take the area of those boxes, because we know how to take the area of rectangles, and we would add all of those up on an interval, and that would get us the area of a function, roughly. It approximated, right? Now, what we do today, and I'll draw another graph, is kind of a calculus version of this. We got here eventually. We started taking infinitely thin slices, infinitely thin box areas, and we would take all of the areas of those infinitely thin boxes and we'd add them up over an interval, and that's what integration is, right? Now, it's weird because the area of an infinitely thin rectangle actually is 0, in fact. However, over an interval, we can use integration techniques to add up all of those infinitely thin boxes and come up with a numerical answer. Or, in some cases, an answer represented in terms of a function, right? And so eventually we got there. We can now, today, with integration techniques that we'll go over in a future video, in future videos, there are a lot of them, take the area of infinitely thin boxes, add them all up, and get a value of area, right? Which really helps us take antiderivatives, or derivatives in the opposite directions. Similarly, because I already addressed this, we can take derivatives, we can go backwards with integration, or take an antiderivative, as formally called, right? Integration and antiderivative are synonymous; they are the same, right? So, kind of like the mathematicians did throughout history on this channel, we're going to go through old methods of calculating area because they are important to know in case you actually don't know how to integrate a function or cannot. And then we're going to go into more formal integration techniques. And I don't want this to be too daunting or stressful for some of you. So I said we're taking all these areas of boxes and adding them up. It's actually going to be more work intensive at the very beginning than it is when we go on until we get very far down the line and do some pretty advanced stuff. We're not actually going to manually add up every single area of an infinitely thin box. We have integration rules, much like we have derivative rules, as kind of a shortcut. Like we have a power rule and a product rule and a quotient rule. We have integration rules that are very similar and kind of correspond to the same things. And then we're going to go over some other mathematical techniques. Anyways, I will stop yapping. It won't be that bad. However, at the very beginning of history, in mathematics, they did actually add up all the areas of the boxes manually because they had to. And that's what we will do because there's no real trick for taking physically comprehensible boxes and adding up those areas. There's no shortcut for that, right? Now we're going to go over some terminology that will be important mostly in the next video, right? Formally, and I'm going to erase all this, the kind of box method of obtaining areas of functions are called Riemann sums. Remember when I drew out the boxes that actually had finite areas, right? Such as this. When I drew boxes like this, we can add up these boxes and get Riemann sums. That's what they're called. Okay, and I'm going to finish drawing this out. There's going to be an interesting pattern you might notice now, or you might not notice. That's okay. There are many different types of Riemann sums, really a few, 4 that we're going to mainly talk about, but they're mainly classifications of how we're actually ordering these boxes, because what really matters is that we have to be consistent. We have to do follow similar steps for each kind of box we draw up here. Now, what I drew is called a left-hand sum, right? And that's one of the classifications we're going to talk about. We're going to talk about probably, I believe, 6 today, right? This will be kind of the introduction of Riemann sums. Next video, we'll probably do some calculations or examples, or maybe not. Maybe this video will just be good enough on its own. Also, since we're doing math now, let's get this on. Gotta be prepared. Okay, so how do I do this? We're going to talk about left-hand sums. Left-hand sums, I'll just write left. We're going to talk about right-hand sums. Can you all see this fine? Yes. Okay. Left-hand sums, right-hand sums, and those are related, very much so. And then we're going to talk about upper sums, and then lower sums. Those are related. And then we'll talk about middle sums. And then last but not least, certainly trapezoidal. Middle and trapezoidal, not super related. They're kind of their own thing. But left-hand, right-hand sums are related. Upper and lower sums are related. Okay, and they're all classifications of these boxes where their ends touch the graph where they meet over an interval. I'm going to call this 0, how many? 1, 2, 3, 4, 5, 6, 7, 8, 9. Okay, I drew 9 boxes. Let's just, for the convenience, make this 9, right, on the x-axis. And this is going to be the f of x-axis, right? Okay, so in this case, I drew 9 boxes, each with a width of 1. We're going to call all of these boxes 1. They each have a base of 1. I know I did not draw that perfectly, but they're all going to have a base width of 1. Because when we're going to do an area calculation, we can find an area, which I'm going to abbreviate as like A. And what we're going to do is we're going to compute the areas of these rectangles, and it's going to be 1 times, and then whatever the height of these areas are. And these over here are going to help us distinguish the height. Left and right hand sums are also going to help us determine actually the endpoints of our graph, of our boxes rather, where they line up with the graph. Okay, I'll erase this, we don't need this right now. So, left-hand sum. When we draw these boxes, we have to start somewhere. Now, what a left-hand sum is telling you is we're going to put the top left corner of a box on the function. That's the part that goes on the curve, right? So I'll draw that here. We're going to draw a box with our predetermined width, because when we do Riemann sums, we're going to have a predetermined width that we think of beforehand when we draw these, right? We're going to start in the top left, and we're going to draw our width, and we're going to draw our box. And then we're going to go over to the next kind of tick mark, I guess. We're going to go all the way up to where that input value strikes the function, and we're going to start our box there. Now, we're going to do the same thing for every single box that we draw. Now, it is important with a left-hand Riemann sum or a left Riemann sum that you start on the left side of your interval, because from here we're getting the area from 0 to 9, right? We're going to start on the left side of the interval and move our way to the right, or right. So, with the right-hand Riemann sum, it's going to be the opposite. I'll kind of draw a little replica here. I'll just draw that on a line. We're going to start on the right side of our interval, and we're going to make our the top right corner of our box on the function, and then we're going to draw our box, right? And then we're going to do that for the entire interval, right? And that's going to be the estimation of our area. Okay, so this is going to very well take us into the next part, right? An upper and a lower sum. Now, upper and lower sums are going to talk about whether our boxes are going to overestimate or underestimate the actual area of a function, right? An upper sum indicates that it is going to be an overestimate, right? Oh, this marker just totally died on me. Okay, let's get this one. Upper sums are going to tell us this is an overestimate, and lower sums are going to tell us that we're dealing with an underestimate, right? Now here, on this right-hand Riemann sum that I drew, this is an upper sum, or an overestimate, because you see all of the boxes, their areas go above the graph, right? And so for this entire interval, this is going to be an upper sum, right? Now, look over here for me real quick. Right until about this point, we're dealing with a lower sum, because the areas of our boxes don't entirely encompass the function. There's going to be kind of some leftover room, right? So we know for a fact that this is going to be an underestimate. Now, upper sums, lower sums do not directly correlate with left and right Riemann sums. Not every right Riemann sum will be an upper sum, nor a lower sum, right? And the same is true for the left Riemann sum. Not every left Riemann sum will be an underestimate, nor will it always be an overestimate. They are completely independent, right? They are two separate classifications, but within their own categories, they're related, right? Okay, so we know now that left and right-hand Riemann sums are going to tell us how we're drawing these boxes, right? And upper and lower sums are going to tell us if we're going to draw boxes that overestimate our area or underestimate our area. Now, sometimes you can be given the information, okay, draw an upper Riemann sum. Now, on this graph, if I wanted to draw an upper Riemann sum, I would have to draw a right Riemann sum. Because if I started, for example, using left Riemann sums, I would get an underestimate because the tops of my boxes would always run under the graph, right? Because the Riemann sum box is going to intersect with the function on the left side of the interval, right? But with the right Riemann sum, we're starting on the right and we're moving left. So as such, the right Riemann sum will overestimate and be an upper sum, right? And you can also be given the information, okay, draw a left Riemann sum, and you might be able to tell if your Riemann sum is going to be an overestimate or underestimate, like I did here, kind of on these first four. If you draw a left Riemann sum, I know that I will be drawing a lower sum. Now, upper and lower sum can change throughout a function, as they did here. We went from a lower sum to an upper sum, back to a lower sum kind of at the very end here. However, left and right Riemann sums cannot change. Do not change from left to right in the middle of your function. You might mess up. Actually, you probably will mess up if you're being asked a question, graded, all that stuff, getting credit, right? We're not going to be dealing with Riemann sums for long. This is an important history lesson, and it's a useful tool in case you ever need to kind of manually bash an area of a function, right? And now before we move on to middle and trapezoidal sums, we're going to talk about how we can reduce the error of our approximation, right? Get an answer that's closer to the actual answer, right? So, as I said earlier, mathematicians eventually started taking infinitely thin boxes and taking the areas of those boxes, adding up all of those, and coming up with a definite exact area. So, we can simply draw thinner boxes, but draw more of them and come up with a more accurate area, right? If we draw larger boxes and fewer of them, we're going to have a less accurate area approximation, right? And so now, lastly, we can use middle and trapezoidal sums as other methods of reducing error, or simply using another method of approximation, right? Middle trapezoidal, these are totally different. Middle sums, trapezoidal sums are totally different. However, these are all methods, upper and lower sums are not related. Middle and trapezoidal sums are related to left and right Riemann sums, right? They're going to talk about how we're drawing them simply, right? And middle and trapezoidal sums are both generally going to reduce the error of our calculation. Now, I am actually just going to erase all of this, draw a new graph so that I can show you guys middle sums and trapezoidal sums. They're pretty self-explanatory. You could probably already anticipate what they're going to show. Hopefully this works. Okay, so a middle sum. A middle sum is going to be a way we draw a function much like a left or right-hand Riemann sum, that such that the middle of our box aligns with the function, right? So let's say we have an interval, actually 0 to, I don't know, let's say 4 this time, right? It's going to be where 2 would be at, and this would be 1 and 3, right about there, right? Okay, so our first interval, 0 to 1, we can take a middle sum, and what's going to happen is that right here at 0.5 is where our box will line up with the function, or will intersect the function. And then we're going to take the area of that box to use in our Riemann sum. And then same for over here, at 1.5, our box will intersect the function, right? And now, most of the time what you see with middle sums is that you're gonna have part of it that's over the graph and part of it that's under the graph. That's gonna happen most of the time. But that actually reduces our error a lot, because kind of the overestimating part of this box is going to be supplemented or complemented by, or at least compensated for, by this underestimated portion, right? And usually they kind of roughly cancel out, not entirely though. Now, there is a formula for this. Well, it's kind of intuitive. What you're really going to do is you're going to do 1 minus 0 divided by 2 for this interval here. You're going to do like final minus initial over 2, and that's going to get an average of the the two endpoints of the interval you're looking at, right? So for 2 and 3 here, we would add 3 minus 2 divided by 2. Wait, did I do that right? No, 3 plus 2, my bad. We're taking an average here, which is going to get us 5 halves, or like 5 halves is going to be 2.5. Right, I'm slow today. Okay, and yes, 2.5 is right in between 2 and 3. We're taking the average of our endpoints, and that's going to get us where that middle value is. I'm going to draw up to the function. The middle of the box will intersect with the function. Okay, trapezoidal sum. In my opinion, trapezoidal sums are probably the hardest. However, trapezoidal sums are oftentimes the most accurate, which kind of sucks for us because we like to be accurate, but we also want things to be generally pretty easy, right? I'm going to draw a function like this, right? This might not work very well, but we'll see. Okay. I'm just kind of drawing out my intervals here, 1 to 5. So a trapezoidal sum, both ends of our box are going to touch the function, right? We're actually drawing a trapezoid. We're no longer drawing a box or a rectangle, right? So we're kind of combining the left and right Riemann sum. This will be 2, 3, 4. Okay, sorry, I was just drawing out the tick marks there. And I know this video is getting long. This is probably going to be one of the longest videos we ever have. But and I'm going through this kind of slowly, but it is a big topic. Integration is very, very, very large, right? Especially Riemann sums. Now, we're going to start on the left side of our function, put a point there for our box, go to the right end of our interval, do the same thing, and then we're going to draw a line between them, a secant line, a straight line right between them. And then we're going to finish out our box by drawing these long legs here. And we just drew a trapezoid, right? And the trapezoidal sum very, very accurately is going to approximate the area of our function, right? But you have to take the area of a trapezoid. That's going to be 1/2 base 1 minus base 2 times height. I'm pretty sure, because if you think about it, it's going to be the height of the function, which is going to be this. This is going to be your height. This is going to be base 1, base 2. It's base 1 plus base 2, my bad. Yes. Because if you think about it, what this formula is doing is you're going to essentially take this trapezoid, you're going to double it and flip it over and then make a giant rectangle, take the area of that giant rectangle, divide it in 2, and you get the area of the trapezoid. So yes, okay. That is the area of your trapezoid, and if you're doing a trapezoidal sum, you're going to have to do this for every single box, right? I'll go ahead and draw out every single box, and as you see, they're pretty darn accurate, right? Except for maybe 4 to 5 here, but I also kind of messed up the interval. Because generally that line you draw for the trapezoid is going to be really, really close to the function throughout the interval. So trapezoidal sums are going to be generally your most accurate way of using Riemann sums to approximate areas. With that is all I have for you guys today. Maybe a few more clarifications. Middle sums can be both upper and lower sums, and trapezoidal sums also the same thing. If you ever get to choose, 1, probably don't choose a trapezoidal sum because it's difficult. 2, you're probably not going to want to use a trapezoidal sum on an interval like this. That would be kind of weird. Probably want to use like a left-hand sum and then maybe break it up further if you want accuracy. Because with trapezoidal sums, while you can be either or both of an upper or lower sum, you probably want to stick to 1 for accuracy, right? With middle sums, you want to have both an upper and lower sum in your approximation, and that's going to happen almost every single time. So with that, yes, that's all I have. Those are kind of the basics of Riemann sums. If you would like to, you can. It's really easy to come up with these problems. Actually, you can make a function, I would start off with something simple like x cubed 4x to the fourth minus 3x cubed plus 2x squared plus 1, right? And then kind of choose an interval, make a Riemann sum for that interval. It's pretty easy to come up with a question and practice that. I might make a community post kind of that if I feel like testing you guys, but it's important mostly to just understand this terminology. You're never really going to be asked in mathematics to take a Riemann sum much, but do understand that this is eventually going to become integration later in history, right? Very clever way of using areas to approximate accumulations of change, and accumulations of change are going to show us kind of how our slope is changing and how that change of slope corresponds to, areas, and how that change of slope is going to influence the growth rate of our function, right? All of which can be related through derivatives, antiderivatives, and of course the original function. I hope this is pretty understandable. I know this is a very, very long video. I yapped a lot. Wasn't necessarily the most coherent the whole time. So if you have any kind of questions or clarification, maybe leave a comment. I'll probably respond to that pretty quickly. So anyways, thank you for joining me on this long and important lesson. I hope you stayed with me this whole time. This is kind of important, but we're not going to talk about it much more. Anyways, I hope you like this introduction to further and beyond calculus. Goodbye.